Good afternoon, and welcome to Hand-Wavy Chemistry, where we do not delight in the details, but rather bask in the big picture. Today, I would like to talk to you about absolute zero, the coldest possible temperature. Now, the idea that there is an absolute cold can feel rather unintuitive, and even more surprising is that we live so close to it. Minus 273.15 degrees Celsius is the coldest possible temperature. However, we can have flames and forges and furnaces around us that go up into the thousands of degrees, and then we have stars which go up into the millions of degrees. So what is absolute zero, and how can we determine it? The first really good experiment that determined a value for absolute zero was conducted over 200 years ago. It used what's known as an air thermometer. If you imagine taking a frictionless piston, like a really well-greased glass syringe where the plunger can move back and forth very easily, and you seal one end of it so nothing can get in or out from inside. You lie it on its side and you begin to heat it. And as you heat it, the syringe plunger begins to move out. And you can record the temperature and the volume, and you can change the temperature, take a new reading, and move it back and forth using heat, using temperature. And then when you plot those results, you find a linear relationship between the temperature of the gas inside that syringe and its volume. If you extrapolate it back to colder and colder temperatures, eventually you will reach a volume of zero. And if you were to go back any further, the volume would become negative. Clearly, you cannot have a negative volume. So this was an experimental way to show that there is theoretically some minimum temperature that you could not go below. And this experiment gave a value of minus 273 degrees Celsius. We can understand how this works if we look at the ideal gas equation. PV equals nRT, piv nert, the pressure of a gas multiplied by its volume equals the number of moles of gas molecules times the gas constant multiplied by the temperature. For this piston, this syringe, our gas thermometer, the pressure inside is a constant because the only thing pushing on the plunger is the air, the atmosphere, and its pressure is not going to change. So the pressure inside is constant. The number of gas molecules inside is also constant. There's no way for them to get in or out. The gas constant is, by definition, a constant. So the only two things that can vary are the volume and the temperature. So from this equation, we can see that the volume would be proportional to the temperature. There's an additional experiment that can be done if we look at this equation again by saying, well, what if we kept volume constant and allowed the pressure to change with temperature? To do this, you would need a sealed vessel and a way to measure the temperature and the pressure inside. Then all you have to do is vary the temperature and record the pressure. This experiment is often done by first-year university students, and I've seen it demonstrated in high school as well. And in the case of the first-year university students, they generally will find that linear relationship between the pressure and the temperature and a value for absolute zero that is within about 50 degrees of the accepted value. The problem with only using these methods is that they rely on the ideal gas equation holding across all those temperatures. We said it doesn't make sense for a volume to go to zero or negative. Well, what happens to volume close to absolute zero? Does it remain linear or will it deviate? Same with pressure. As we start to vary the temperature, how true is that linearity? So we need another way to think about absolute zero and determine it. Luckily for us, there's thermodynamics. If you rub your hands together, you can feel them getting hot. You are doing work and generating heat. It is also possible to use heat to do work. Let's think about a car. It doesn't matter if the car runs on petrol, diesel, or electricity. It has a tank, a reservoir of energy that it uses to do work. If the car runs out of energy, it runs out of fuel, that reservoir is depleted, it can no longer do work and it will stop moving. In a similar way, we can think of matter, atoms and molecules having a reservoir of heat energy. They can use it to do work. And if they run out of that heat energy, they will no longer be able to do work. When Lord Kelvin used this approach to calculate the value for absolute zero, he found it to be minus 273 degrees Celsius, the same as was found using the air thermometer. Since that time, researchers have continued to refine their estimates for absolute zero. Currently, it is defined as being minus 273.15 degrees Celsius. And experimentalists have tried their darndest to get right down to that temperature, and they've gotten very, very close, never quite reaching it, and they certainly have never gone below it. Now, you may be wondering what happens to matter at these extremely cold temperatures. And you may even have heard of the term Bose-Einstein condensate. Well, that is a story for another time. I hope you have enjoyed this video. And if you have, please make sure to like, subscribe, and share it with your friends. And if you have any suggestions for a future topic to be covered, please put it down in the comment section below. Thank you, and I hope you have a wonderful rest of your day.